Last month, a major financial services company got breached. The attackers didn't hack through their firewall. They stole one employee's VPN credentials from a phishing email, logged in, and because they were now inside the network, they had access to everything: customer data, financial records, internal systems, all because the company trusted anyone who made it past the front door.
Wait, so their security was basically like a castle with a moat? Once you cross the drawbridge, you can wander anywhere inside?
Exactly. And that's the fundamental flaw we're going to tear apart today. Welcome to CloudCast. I'm your network ninja, and today we're diving into zero trust architecture, the security model that says never trust, always verify. By the end of this episode, you'll understand why the castle and moat approach is dead and how to actually implement zero trust in your cloud environments.
I've heard zero trust thrown around a lot, but honestly, it sounds like marketing speak. What does it actually mean technically?
Fair skepticism. Zero trust is a security framework originally defined by Forrester research analyst John Kindervag back in 2010, and later formalized by NIST in special publication 800-207. The core principle is this: no user, device, or network segment is inherently trusted, regardless of their location. Every single access request must be authenticated, authorized, and encrypted before granting access.
So even if I'm sitting in the corporate office, on the corporate network, I still have to prove who I am for every resource I access?
Precisely. Let me give you an analogy. Think of a high-security government building. In the old model, you'd show your badge at the front entrance, and then you could walk into any room. In Zero Trust, every single door inside that building has its own badge reader. You need to authenticate at each door, and each door checks whether you specifically should have access to that specific room at this specific time from this specific device.
That makes sense, but doesn't that add a ton of overhead? Like, wouldn't everything be incredibly slow if you're constantly re-authenticating?
Great question, and this is where the analogy has limitations. In practice, zero trust doesn't mean you're typing passwords constantly. It means the system is continuously evaluating your access through automated policy checks. Modern implementations use short-lived tokens, continuous authentication signals like device health and user behavior analytics, and policy engines that make decisions in milliseconds. AWS IAM, for example, evaluates policies in single-digit milliseconds.
Okay, so what are the actual components that make up a zero trust architecture?
NIST 800-207 defines three core logical components. First, the policy engine, which makes the access decisions. Second, the policy administrator, which establishes and terminates connections based on those decisions. Third, the policy enforcement point, which is the actual gateway that allows or blocks traffic. In AWS terms, think of IAM as your policy engine, AWS organizations SCPs as policy administrators, and security groups plus VPC endpoints as enforcement points.
Okay, so let me make sure I understand. So if I'm an application trying to access a database, instead of just being on the same subnet and having access, I'd need to go through some kind of policy check first.
Exactly right. Let's walk through a concrete example. Say you have a web application in a subnet with CIDR block 10.0.1.0/24, and your database is in 10.0.2.0/24. In the old model, you might have a security group rule allowing all traffic from 10.0.1.0/24 to port 3306 on the database. Any compromised instance in that subnet could access your database.
And in zero trust?
In zero trust, that application would need to authenticate to an identity-aware proxy or service mesh. In AWS, you might use IAM roles anywhere combined with VPC Lattice. The application presents a certificate, IAM validates the identity, checks policies like, is this the production web app? Is it running on an approved instance type? Has it passed its last security scan? And only then does VPC Lattice allow the connection to the database on port 3306. The database itself also validates the connection using IAM database authentication.
So you're layering multiple verification steps. What about Azure and GCP? Do they have equivalent services?
Absolutely. Azure has Azure AD conditional access for identity verification, Azure Private Link for network-level enforcement, and Azure Policy for governance. GCP has Beyond Corp Enterprise, which is actually Google's internal zero trust implementation that they productized. It includes identity-aware proxy, VPC service controls for creating security perimeters, and context-aware access policies. All three clouds also support service mesh implementations like Istio, which provides mutual TLS between services.
You mentioned mutual TLS. Can you explain what that means in this context?
In standard TLS, like when you visit a website, only the server proves its identity with a certificate. Your browser verifies the server is who it claims to be. In mutual TLS, or MTLS, both sides present certificates. The client proves its identity to the server, and the server proves its identity to the client. This is critical for zero trust because it ensures both ends of a connection are verified. In Kubernetes environments, service meshes like Istio automatically inject sidecar proxies that handle MTLS between all services.
That's really powerful. But I'm curious, what are the biggest mistakes people make when implementing zero trust?
The number one mistake is treating zero trust as a product you can buy rather than an architecture you implement. Vendors love to slap zero trust on their products, but buying a zero trust firewall doesn't give you zero trust. You need to implement the principles across identity, devices, networks, applications, and data. The second major mistake is trying to boil the ocean. Organizations attempt to implement zero trust everywhere simultaneously and get overwhelmed.
So what's the right approach?
Start with your most critical assets. Identify your crown jewels. Maybe it's customer data, financial systems, or intellectual property. Map all the access patterns to those resources. Then implement zero trust controls around those specific assets first. Google's Beyond Corp implementation took years, and they started with internal applications before expanding. NIST 800-207 actually recommends a phased approach, starting with enhanced identity governance, then microsegmentation, then software-defined perimeters.
Can you walk me through what a real implementation might look like? Say I'm building a new application in AWS.
Let's design it together. You're building a 3-tier application: web frontend, API backend, and Postgres database. First, identity layer. Each tier, it's its own IAM role with least privilege permissions. The web tier's role can only invoke specific API gateway endpoints. The API tier's role can only connect to RDS on port 5432 and only to specific databases. Use IAM roles for service accounts if you're on EKS, or instance profiles for EC2.
What about the network layer?
Each tier lives in its own subnet. Web tier in 10.0.1.0/24, API in 10.0.2.0/24, database in 10.0.3.0/24. But here's the zero trust part. Security groups don't reference CIDR blocks. Instead, they reference other security groups. The database security group allows inbound on port 5432 only from the API tier's security group ID. Even if an attacker compromises a web server and somehow gets into the 10.0.2.0/24 subnet, they can't access the database because they're not running with the API tier's security group attached.
And you'd add VPC endpoints to avoid traffic going over the public internet.
Exactly. Interface VPC endpoints for services like Secrets Manager, where you're storing database credentials. Gateway endpoints for S3 if you're storing application assets. Each endpoint has its own endpoint policy that restricts which IAM principals can use it and which resources they can access through it. You're creating multiple enforcement points, and an attacker would need to compromise identity, network, and application layers simultaneously.
This is clicking for me now. It's not about one security control. It's about layering controls so that compromising one layer doesn't give you access to everything.